If you click on the link in Sakai, it brings you to this page, and then you click here and it opens the simulation for you. What you see are two masses, a blue one and a red one. They're held in place by these little stick figures. You have two sliders which allow you to change the masses, and up above you are shown the value of the force because the show value button here is clicked. And notice force on M1 by M2 is a number. There's lots of zeros, and then a 3963 in this case. The force on M2 by M1 is lots of zeros and the same set of numbers, 3963. Both are in newtons. If you didn't pick up on it, these are a third law force pair. The force on M1 by M2 and the force on M2 by M1. Here are the flipping of the subscripts. One thing you're asked is, can this force ever be repulsive? If we look, no matter how I move the blue mass relative to the red mass, the force on the blue mass always points towards the red mass, indicating that it is attractive. So you cannot get a repulsive gravitational force, and really this is because you can't have a negative mass. That's what it would take to get a repulsive magnetic force. So I'm going to put this guy back over here, say at 0. And now the question is, what happens if I double a mass? So if I take the 25 kilogram mass and make it a 50 kilogram mass, what will that do to our force? Currently our force is lots of zeros ending in 1301. If I double the mass and put it at 50, I have lots of zeros and ending at 2603. 2603 is roughly double 1301. My guess is there's some round off going here, which is why it's not exactly double. Okay. Next question. If I take, I'm going to bring them really close together for a minute here, and double the distance. So right now we have a distance of about 2 meters, and we see a force of lots of zeros, 32020. Okay. Now, if I double the distance, that means I take this guy that's at 2 and I move him to 4. What does that do to my force? Instead of being at 32020, I'm now at 8045. Okay. So I changed the distance by a factor of 2. I made it 2 times bigger. And I see that the force has gone down by a factor of 4. Okay, so let's do another one, just for the sake of looking at it here. At roughly 3 meters apart, I'm at 14,571. And if I double the distance, that means it goes from 3 to 6. And my force has gone from being 14,571 to being 3,570. If you pull out a calculator and punch it in, 14,571 divided by 3,570, indeed, that is again about a factor of 4. Okay. So if you increase the force, let me try that again. If you increase the distance, the force decreases. And when the force decreases, it does not decrease by the same factor. You double the distance, the force goes down by a factor of 4. If I were to triple the distance, I would see the force would go down by a factor of 9. So let's try that really quick. So at 3, I'm at 14,770 again. And if I make it 9, I end up at 1576. If I take 14,770 and divide by 1576, I get a factor of 9.4, and it's not exactly 9 because I wasn't exactly at 3 and not exactly at 9, but it's close. Right? This is known as an inverse square law. Okay, it's inverse because you're going to see that the distance dependence is in the denominator of our function, and it comes in squared. So when I increase the distance, the force is going to go down, and it's going to go down by the square of the amount that the distance was increased. Conversely, if I decrease the distance, so when I go from 9 to 3, I see that the force increases, and it will increase by a factor of 9, or the change in distance squared again.